In this episode, we're going to do battery testing. We're going to be going through talking about all the different batteries that you can get from the junkyard, what kind of power you can get them. That's why we got the airplane up top and the beamer down below, because we're going to use this for battery testing. We are taking data, but we're still in the barn. The reason for that is that it's very snowy outside, so we can't test. So we're going to have to go with plan B. What does B stand for?
Burnouts!
Alright, here we go. Well, I think that was a successful test. Barn door is still in place. We got our data. Remember, this was for science. Up to 600 volts.
Motor repair, take one. These 4 bolts here.
That shaft moves this lever. It's alive! Alright, I know what you guys are thinking. Carrie, you're crazy. Why are you doing burnouts in a BMW in the barn as opposed to working on the electric airplane, which is what this series of videos is about? Well, one, it is kind of fun, but realistically I do actually want to get some battery testing. So in this video I'm going to run you guys through a selection of batteries here, most of which are from a junkyard, and kind of talk about if you're doing a budget build, what kind of batteries are out there, what are some of the pros and cons of it. Alright, let's stop right here. You're about to listen to me drone on for 15 minutes pointing at batteries and just talking about things. Well, I'm an engineer. I like numbers. Let's let the numbers do the talking. So I have this Excel threw together, and we have the Model S, the Smart EV, the Volt Gen 1, Gen 2, as well as the Leaf and the Pacifica. I also have here the Bolt Model 3, Kia, and 500e, but I don't have any experience with these. I'm going to throw this Excel file onto my Git account. So if people have information on this and they want to contribute, by all means, fill out the numbers for that. I'd love to get my hands on a Bolt or a Model 3, but sadly that hasn't happened yet and not within my budget currently. Anyway, so we got these 6 batteries here, and we've got the kilowatt hours, the kilowatts, so battery can only put out a certain amount of current, and with that combined with the voltage, you can figure out how many kilowatts you can put out. Now, how much current puts out is a hard thing to really answer. It depends on your application. If you're just outputting for 10 seconds, you can do a pretty high current discharge, but if you are wanting to discharge the pack for 30 minutes or something like that, it's going to be a very different number, assuming you even have that capacity to do that. So this current, take it with a grain of salt. In your application, like in the Model S, the cooling's not great on it, so it may end up overheating if you do 750 amps for too long of a time period. Like the Smart doesn't have cooling. Gen 1, Gen 2 volts have very good discharge rates. The Leaf, common problem is it doesn't have any cooling. So anyway, there's that. All the information I put in here, capacity, number in series, and number in parallel, the weights that I've measured in this video, and we can calculate the volume. You could calculate volumetric efficiency. That's kind of important, but that's usually not the real critical thing for most vehicles, so I'm not going to dig into that too much here. I did turn all the energy density and weight densities or power densities into kilowatt hours or kilowatts per kilogram. Apologize for the mixed units. Here in U.S., unfortunately, we still use yield unit system, while the rest of the world will appreciate the kilowatts per kilogram because that's a standard unit of measure. Also here I have the market price Obviously, this is just an average my take. You can get things for cheaper, especially if you find them local, or you can find them for a lot more expensive as well. This is just my rules of thumb for price. Obviously, your mileage may vary. But using that price, we can look at dollars per kilowatt hour and dollars per kilowatt. So these are the things that that we want to look at. And also in this chart is the places you can get it from. eBay, EV West actually carries a lot of these batteries. They're great guys to deal with. Junkyards, or go on to Carpart and you can find stuff. So with that, let's jump into energy density. So energy density, like talk about in the videos, the cells can be set up differently. So you can tailor them, the anode and the cathode and the chemistry to get a high energy, or you can tailor them to get high power, or you can get a compromise between the two. Tesla Model S has a huge pack, so it doesn't need much power density, but it needs a lot of energy density. So we've got, it's got the best by far. This number will vary from year to year for all of these. As companies are making incremental improvements, they'll roll out new batteries and make improvements there. So this will vary some, but for the most part, it's good. You can see the lowest energy density actually here we have is the Gen 1 Chevy Volt cells, and the highest are the Tesla. The rest are all really about the same range, unless you're really, really weight critical like an airplane, it's not going to matter. But we come over to power density and we see big differences here. And this comes back to that tailoring of the battery specifically for what your application is. So the Gen 1, the Gen 2, and the Pacifica all have very small battery packs, but they're pushing around full-size vehicles. And like Gen 1, Gen 2 volts, those are around, all these are about 15 kilowatt hour packs, but they still need to pull out full power. So they are more power-driven cells. You can see that Gen 2 volts are about the best, but really it's in the noise with the Pacifica, especially if you had to take into account the cooling system that you need. The leaf is very poor. It's also not very, what we call stiff cells. They tend to sag quite a bit. Likewise, the Smart EV and the Model S. You say, wait, Model S doesn't have much power. How can that be? The Model S is, you can get a P90D and smoke just about everything out there. You can, but they have huge battery packs, like 1,200 pound battery packs or more, and that battery pack weight. Or that large battery then allows you to not have to discharge the cells nearly as hard because you've got just so many cells to deal with. So the real telling one is we come over here and we'll look at the combined. So this chart, and same thing as the previous ones, just overlaid to each other. So gray, you can see if you want max energy density, you come in here and get the Tesla cells. But then if you have to consider what you need for power density, Teslas might not work because you have a much lower power density, as you can see on this axis. So if you're doing a small pack and you still need a lot of power, or even a medium-sized pack and you still need a lot of power, that's probably not going to work for you. But if you want a large pack and you want a lot of range, you want the highest energy density that you can get. And so that's what's going to push you over to the Model S's, or the go-tos for that. The power cells here, see the Gen 1, Gen 2 volts, and the Pacifica. Gen 1 and Gen 2 volts are, Gen 2 volt and the Pacifica, very, very similar in performance. Like I say in the video, I think, I wonder if it's the same chemistry, just reconfigured. They're both, all three of these are LG Chem pouch cells. The Nissan Leaf is kind of the laggard. It has very poor power density, and it has mediocre energy density. And it's the Pacifica is nice because it doesn't have any of the diff challenges with liquid cooling. It's just an air-cooled pack. So with that, now we'll look at the what you get for your dollar as far as kilowatts and kilowatt hours. Now I threw this chart together. I hesitate actually putting it because the price is going to be so variable depending on where you are, where you're buying from, shipping included, etc. But at least kind of a starting point of what you can deal with. Obviously, you can potentially find better deals, or you might not be able to find deals this good. But anyway, so same chart as the energy and power density, but it's just done on $1 per kilowatt hour basis. So here, this is how much you have to spend to get 1 kilowatt hour, as shown in orange, or 1 kilowatt, as shown blue. Lower number the better. That means you're getting more kilowatt hours for, getting that kilowatt hour for less money. So we'll start with the Model S and the Smart. They're on about the same footing as far as dollar per kilowatt and dollar per kilowatt hour. They're definitely on the high range. Part of this is, like I mentioned, people know what Tesla packs are, and they're kind of the ones that everybody seems to want. So some supply and demand dictates that the prices are higher. They're also hard to get a hold of, I found in my experience. They're really hard to find through Carport. Next up, we have the Chevy Volts. Obviously, it should be pretty clear here why I've been using a lot of the Gen 1 and Gen 2 Volts. Is even with the prices having increased, you're still getting a very good deal on dollar per kilowatt hour. You're getting a very good deal on dollar per kilowatt. So you get a lot of power for not a lot of money. Again, money isn't everything. If you need a lot of energy, your pack's going to weigh too much, and etc. But that's if you're doing short duration racing, then this is great because you can get a lot of bang for your buck. The Nissan Leaf's there. It's got pretty low power cost and a pretty low energy cost. This is all without degradation. So realistically, you might be losing this number. Could be going up steadily, depending on how many miles are on the Leaf and how they've been treated. And then finally is the Chrysler Pacifica. These are harder to find, so you're certainly spending more money on them versus the Gen 1 and Gen 2 Volts. But it has the other advantages of simplicity and energy and power. But shop around. The best deal you can find is if you can find a local junkyard that has it, because you're not paying for shipping costs. Shipping on these things aren't cheap. But in the end, you're not going to, unless you're doing a ground backup storage, you're not going to pick based off of this for an actual EV. You're going to be more driven to your application of, do you need more power or do you need more energy? So that'll dictate a lot more about your vehicle, whether you what batteries that you're going to go with. So with that, let's go back to the barn.
Is that the Tesla modules are made of cylindrical cells. They're pretty much the only ones that use it that are in mainstream AVs. A lot of the real high-end ones will also use the 18650s. I'm not going to tell you about this part. I'll show a picture right now, but just think of an oversized AA battery. Has some advantages and disadvantages. Advantages in construction and on the manufacturing line. Some disadvantages as far as assembly. There's a lot more. The cells are smaller, so there's a lot more contacts to make. The other one is that it's harder to cool. So they have these silicon lines that they actually run through, back and forth through here. That means you're only cooling part of the cell, and it's hard to get that heat out. So if you're really, really hammering these cells, the pack's going to start to overheat. There's thermosistors in the pack that will actually measure the cell voltage if you're using the BMS, which you probably should be. And then it will go into a thermal protection mode to keep you from overheating the pack and catching things on fire, which is a good feature. So we got 55.44 pounds. Again, very good energy density, but for my application, the power I would need out for this just to power my Challenger, which is not a very heavily powered vehicle, I would need 2 of these. So over 110 pounds, plus cooling system, plus mounting, etc. It adds up pretty quickly. So I mean, you're probably looking at 125 pounds to get that 10 kilowatt hours. And that's going to put me way over my weight budget. With the Challenger, I have about 40 pounds of batteries that I can carry and still stay under the legal limit, which is what I'm going to do. Like I said, summary, Tesla cells, very good energy density. Unless you're building a really big pack, you're not going to get much power. Great for ground storage. They're an LCA battery. They have good capacity retention. And the disadvantages are that you aren't getting much power. Oh, and one other thing on the Tesla is there's a guy who's hacked the BMS for the Tesla, so you can actually use the onboard BMS board. I'll throw a link to that in the description. All right, next we have the Gen 1 Chevy Volt cells. These were made from 2010 to 2015. They had a capacity change at 2013, so 2013 to 15 has a little bit more capacity. This module here is 2 kilowatts. I know that because conveniently they put on the label 2 kilowatt hours. And so that's, you know, we're talking about less than half the storage energy capacity as the Tesla module. Weighs 38 pounds, so not half as much. So you have significantly less energy density here in the Gen 1 Chevy Volt cells. The nice thing is they have very good power density. So these cells are what we call more of a power cell. So I've gotten 1,000 amps out of this. I've gotten more than 1,000 amps, but I wouldn't recommend doing that. For those of you who watch all the videos of Silent and some of my other EVs, this has been my go-to for a long time. Actually, about 5 years ago, I posted a whole video on how to find the Chevy Volt cells in junkyards. That applies pretty much to all of these, and how to take apart the pack. I'll throw a link down there. Back when I was buying this, nobody wanted the EV batteries. In fact, a lot of junkyards didn't know what to do with them. They were scared of them. So I could pick them up for cheap. I could get an entire 15 kilowatt hour pack of a Volt. I got one for like $700. Now these are going for about $2 to $3 grand, mostly in the $2 grand range, and they're getting up there in miles. So I wouldn't worry about, for the Tesla and the Volt and probably the Pacifica, I wouldn't worry about mileage really that much. Calendar year matters some, but from all the stuff we've seen from those cells, the amount of degradation over the years has been very, very small. Personally, I've got a Volt pack with 120,000 miles, and it's only lost 5% capacity over 5 years and 120,000 miles. And that's mostly EV miles and not just gas. So that degradation really isn't a big factor on the batteries that I'm going to be talking about. I don't have any Nissan Leaf batteries here because I don't really recommend them. They are very prone to capacity degradation. They don't have any heating or cooling, and that's a big issue. All the batteries I talk about here have some method of cooling. That being said, they are liquid cooled. They are pouch cells. So what a pouch cell is, I'll show this is a Chrysler Pacifica battery. Again, Pacifica battery back there. I take this apart, and I'll show that later. But as it indicates, or as the name indicates, it looks like a pouch. These are LG chem cells. LG is kind of the go-to as far as pouch cells are concerned for the OEMs. If you want really, really high discharge rates, I would recommend, we're talking like drag strip, you want to drain your pack in 10 seconds. None of the OEMs are the ones you want. You want to contact Lone Star EV down in Texas. John Metric, he builds really, really good packs for that. This pouch, same construction, is inside here. So there's these series of plastic trays, and inside are the individual pouches. This is one I've used in the EV30 for quite some years. Previous people have seen when they'll throw a link also to the video when good BMSs go bad. Whoa! Wow. I take apart one of these batteries where the BMS drained it down to 0 volts. It's kind of an interesting video, and that gives a pretty good, or some deep dive into the construction of it. But yeah, you can pull about 1,000 amps out of it, so very good power density. Again, low on the energy density. Definitely do recommend the liquid cooling. And again, it weighs, for 2 kilowatt hours, it weighs 38.62 pounds. Gen 2, as you might imagine, more advanced version from Chevy. Again, LG pouch cells, very similar to construction to these trays. These plastic trays are to hold everything in place and allow that liquid cooling. So you've got a port here and an outlet port here. But inside it has these plates. And this is what gets the heat in and out of batteries. So batteries, people want to be treated a lot like humans. They don't want to get too hot and they don't want to get too cold. And you need to have some sort of thermal management system into it. Again, Nissan Leaf didn't have it, and they paid a price for that. But pretty much everybody else has some sort of thermal management system. So what it is this is actually very, very small channels. I don't know if that'll show up very well there. But so very, very small channels here. The coolant comes in, is pressurized, spreads throughout all these little channels, and then comes back in. So you've got huge surface area for a very thin cell. So you can get heat in and out of this very, very quickly. So if you need to preheat your pack, you can do it quickly. But more importantly, if you're really hammering on it, you can get that heat out really well. Oh, a lot of people ask if you can reconfigure these packs, like make more pouches or whatnot. The answer is no, not practically. I mean, you can do whatever you want, but just because you can do something doesn't mean you should. So, 2.3 kilowatt hours. So like I said, it's 15%. Is that right? No. Yeah, 15% increase in power over the Gen 1 volts, or of energy. Should be about the same power, but we'll talk about that in the E30 videos. This is 35.86 pounds. So I've got 15% more energy, and I've got lower weight. So this is a noticeably higher energy density that I want to take advantage of. So this is a 12S configuration. I didn't mention it, but the Chevy Volt Gen 1s, you can get in 6S or 12S, so that's a 24 or 48 volt. They've used different modules depending on where they were in the T-shape pack. Again, go back and look at the videos, previous videos on Gen 1s. I also have the time-lapse video, and I deconstructed Gen 2 Chevy Volt. That's from a few years ago. But what it comes down to is these come in 12S and 16S. The 12S is exactly what I need for the Challenger, so I actually reconfigured my EV30 so that I took two of the 12S out and put one 16S in. So I've got two 12-volt packs, 35 pounds. I should be under my weight limit, and I should have more than enough power output for this. I'm probably going to pull around 500 amps from this. I'd have no qualms about pulling that from this. The biggest thing I don't like about this for the Challenger is that I do have to put some sort of cooling system in. I don't necessarily have to, but that's going to limit your discharge rate. The last one we'll go through here is the Chrysler Pacifica. This is a cooled pack. It's not actively cooled. It actually has aluminum that's put in here just for the sole reason of getting heat in and out. So these aluminum channels are in between each pouch. So again, you got very large surface area, and that allows that heat. Aluminum is very conductive to heat, so it conducts that heat down. And you can put a chill plate here, you can put fins on it, you can put a heater here, so you can actually thermally control these. These are very much set up as power cells, but they also have very good energy density. So 39 pounds, and it's 2.6 kilowatt hour. And you don't have to mess with the liquid cooling system. You can get these, I think, in my mind, as far as a junkyard EV battery, where you want a good mixture of power, energy density, and simplicity, because these are don't have a liquid cooling loop. These are really, I think, the go-to. I'm going to start hammering these through tests. But the disadvantages is for why not use this for the Challenger, I'm trying to decide, is that these come in 16S. I need 12S for the Challenger. We'll show in a bit. You can tear them apart, reconfigure it. Don't. It's not a good idea. There are batteries I didn't talk about here. The Kia made the Kia EV. I've heard good things about that, but I've never played with them myself, and I don't have any data on that. The Smart EV, Smart and Toyota all worked with Tesla as far as coming up with a EV pack. So those are the same 18650 cells. I think on the Smart there's significantly lower discharge rate on power, but I could be wrong on that. They weren't made in large numbers, so they're harder to find. So that's why I usually stick to the Volt or stick to the Tesla, is because they are, you can find them pretty much anywhere, because they did make hundreds of thousands of them in the U.S. So that's the different batteries. Hope you guys found that interesting. Whether you're building an electric airplane or the electric Lemons, I have my Audi Lemons car, but I'm not converting that over to EV. 5-cylinder and straight pipes. You can't replace that with electric. And I don't know. I've got too many other projects anyway. But anyway, I hope breaking it down and splitting packs into smaller ones, like I've done here. Again, you can do it. I really wouldn't bother. You have to have a very, very point design of why you need to do that to make it worth the hassle. All right, so I was going to post the videos of the Chrysler Pacifica battery teardown. I'm still going to do that, but I'm not going to do it in this video because it's already getting long and boring, and most of the people probably tuned out way by now. But anyway, before I show the specifics on the EV30 installation, give a little bit of a background down it. I was slightly exaggerating about the Planet Hoth, but we do have a good 3 or 4 foot snowdrift in the front of the barn and nowhere to go. So it's going to be sitting here. It's Colorado; it'll melt off pretty quickly. But yeah, so let's talk about the car itself. So I converted this over, I don't know, 3 or 4 years ago. If you're actually really interested in the car, definitely recommend go back and look at those videos. I apologize, they're as terrible as the ones I make now, probably worse. Anyway, bought this for $600 off the original owner. This is the third pack this has had. Originally, I installed a set of Enerdell packs. Those went off to a friend's conversion. He wanted them. And then Gen 1 volt packs, had those in here last until the BMS killed it. And now I've got the Gen 2 volts. So they're in there, but right now I don't have the BMS hooked up yet. That's on the list of things to do. Orion actually makes a really nice BMS. I've used several different BMSs and I think they're my favorite. The only problem is you have to deal with the pile of spaghetti to wire it up. Again, my friend actually did all the wiring for that. If anyone's interested, I can give you his contact info. But yeah, so he made up the harness to hook up and just tap into the Gen 2 volt packs. So just took the existing head, cut it off, and then spliced in the Orion BMS. So anyway, past that, I mean, it pretty much looks like a normal E30. And it's really what's under the hood, and that makes the difference. But it's 0 to 60 is in the 5 seconds. I don't have a V-box, so it's just going off the speedometer. In the 5s, which is plenty sporty. I've taken it to SCCA Autocross, BMW Autocross, and it's a real fun car to drive. That's one of my favorite things about electrics is the throttle response. So when that wheel starts to slip, I can just give it a little bit more throttle, break them loose, or back off, and you can really just ride right on that edge. You can really steer with the throttle with a rear-wheel drive electric car that has no traction control, which, of course, this one doesn't. So enough of that. Let's look under the hood. That's a GE 11-inch. That is a beast of a motor. It's hooked up to a Dodge, full-size Dodge truck AX15 5-speed transmission, which I really like. It actually shifts really well. It's hard to believe it's actually a truck's transmission. But anyway, it's a stage 4 clutch. It was essentially the biggest clutch I could find that without spending ridiculous amounts of money on it, and I think it still slips it even with that.
Under the hood, the first thing I had to do was reinstall the Soliton controller I had ripped out trying to make a hero repair for Silent. But in the process, I found something interesting out back.
Alright, I'm under the EV30, and I just wanted to point this out, the high current cables that run up to the front Soliton. And I originally had P-clamps holding them up in place to go over the CV joint. And I had just done a sheet metal screw in there temporarily just to hold it, and I'd come back later and fix it. And of course, out of sight, out of mind, never did that. The screw pulled out, and then it started rubbing against the CV joint. The positive is luckily all okay, but the negative actually wore through down to the cable there. So obviously if it had done that on both, it would have shorted the circuit and would have been a pretty bad day. So I think it's time to make it go. Hopefully I don't turn the garage door into a drive-through. About 500 amps. We got our data. Remember, this was for science. Alright, so I got data. This is the data that was recorded by the Soliton controller, things like pack voltage and current, and I did some post-processing on that to get pack sag and C rate, that kind of thing. So the big thing we're looking at is I pulled about 700 amps out of the battery. That's this light blue line here. And Not saying the batteries couldn't have outputted more, but that was the most that I was able to pull from the batteries in the highly controlled condition of doing burnouts. Obviously, I don't have a dyno. I couldn't put more load onto it. I'll work with that. There's other testing I can do, but for the right now, 700 amps, we could go higher, but it's the data that I have. Now, that 700 amps correlates to the C rate of about 13 C. Now, C rate is the relation of the amp hours of the battery to the amount of current that you're pulling out of it. So in this case, I'm pulling out 13 times more power than the amp hours of that of the volt battery. For reference, the Tesla batteries are at Smart EV and the Nissan are all about 3C, so significantly lower than that. They are not power cells; they're energy cells. The Gen 1 Chevy Volt and the Chrysler Pacifica, it's 20C, so nice high discharge rates and with low sag at that point. Now, 13C again, I could have gone higher. But that was the most power that I could pull from it. Now, the key thing you want to look at these C rates, or what you discharge, is see what happens to the voltage. So this battery pack started off with 285 volts. Then it sagged down to about 230. So what that sag is this relation of the starting voltage versus the voltage under load. The voltage will drop as you start pulling current out of it. And that percentage there is this green line. And I got about 21%, 22% sag at 13C. That is more than I would like, but there's a big caveat to this data. It was a cold barn, and the batteries were in the 40-degree temperature range. Now, that mid-40s is a lot lower than your optimum temperature. Again, batteries want to be warm, somewhere between 80 and 100 degrees Fahrenheit. You can go higher, and depending on your level of comfort, risk, etc. Some people go significantly higher. And what happens is, as the batteries are warmer, then batteries are electrochemical reactions. And that, if you remember your chemistry classes at all, most chemical reactions happen faster when the temperature increases. So you get them warmer, the chemical reactions happen faster, you can output more power, less voltage sag, all great things. That is, up until the point you get the batteries too hot, and those reactions happen much faster than you want in the form of things catching fire. So there's obviously a balance there. Also, the batteries will degrade if you get them too hot and really hammer on them. So it comes down to what you're trying to achieve and what your level of risk is. So with that being said, the 13C and the 21% sag are good numbers for a power cell, given the fact that it was 45 degrees. Now, is that the end of it? No, I'm going to actually do more testing. I'll get the car out on the road, get the batteries up to temperature, get, again, 80 to 100's a good place to start, and then see what that voltage sag is. I don't have any data on any other batteries because I haven't done any other testing when things are cold. All of my racing is between 80 and 100 degrees Fahrenheit, so that's all the data that I have. But do know that how much the electrochemistry is affected by the temperature, and so I would expect to see even significantly better performance this. I'm still going to stick with the 1,000 amps out of the volt module for the time being as kind of my guideline, but until we actually do testing, I won't know for sure. So with that, more data to be had. I like data, and let's go back to the barn.
Well, I hope you guys found that enjoyable. Probably long-winded and not with much electric airplanes in it, but good news is I have both motors and motor controllers on their way, and the next video will be all about the motor testing that I've done, how I came up with and selected the motors that I did, as well as the ESC for the brushless DC motors that I'm using for the airplane. I'll talk about that and have some fun footage to show you on motor testing. But you'll have to stay tuned. That's probably a couple weeks to a month out. But I hope you guys will enjoy. Subscribe, and when the next time video posted, there's probably a button on here somewhere, to subscribe
And if you guys like the video, let me know. Definitely feel free to post things in the comments. Usually on the internet you don't read the comments, but if you guys have other videos you want to see, more information, or places that I glossed over that seemed obvious to me that you guys want more information on, definitely let me know. Thanks.